Hello everyone, today we are going to start section 3.6 Gram-Schmidt orthogonalization. And before we learn how to do that orthogonalization, we need to introduce some definitions. We're going to start with two definitions. Orthogonal set. This is a set of two or more vectors where all vectors in pairs are orthogonal. So if you have like two vectors, they just orthogonal. If you have like 3, 4, 5 vectors, they are orthogonal in pairs. So vector 1 is orthogonal to vector 2, or vector 1 orthogonal to vector 3, and so on. All of them are orthogonal to each other. Orthonormal set, a little difference, the word normal. And this is going to be orthogonal set where all vectors are unit vectors. So unit vectors are an orthogonal set. Let's consider an example of orthogonal set. U1 equals 2, 0, 0, U2 equals 0, 3, 0, and U3 equals 0, 0, 1. So these are three vectors which belong to R3, right? And we are going to see that they all are orthogonal to each other. So if I find the inner product between U1 and U2, and here we have just a three-dimensional normal vector space with normal dot product as inner product, we're going to have what? 2 by 0 plus 3 by 0 plus 0 by 0. We are going to have 0. And U1, U3 is going to be what? 2 by 0 plus 0 plus 0 by 1, which is also 0. And U2, U3, last pair we have, is going to be 0 by 0 plus 3 by 0 plus 0 by multiplied by 1. So this set is orthogonal. All inner products, or in our case, just regular dot products, are equal to 0. All vectors are orthogonal in pairs. Now, how to make this set orthonormal? Example number 2. Well, each vector here is supposed to be a unit vector. So far, guys, we have one unit vector. This is a unit vector. These two other first and second are not unit vectors, but we can always turn them into unit vectors, right? If we divide u1 by 2 and we divide u2 by 3, we are going to turn them into unit vectors, and we are going to have what? Orthonormal set. And this is orthogonal. So, orthonormal set, orthogonal set. Here, guys, I just put a regular dot product, not inner product, just because we are going to have just regular dot product in this, like this specific example. Now, the question is, well, for these vectors u1, u2, and u3, what I did to turn them into unit vectors, I just seen that this is coefficient 2, and if I divide by 2, I'm going to turn it into 1, right? And the norm of this vector is going to be 1 squared plus 0 plus 0. But what if I have just any arbitrary vector? So the question is, how to make a unit vector, sorry, of any vector v, arbitrary vector v. Well, we did it already several times, but just in case you forgot it. Unit vector of any vector v by, we can just check it. You can take vector v and divide by norm of vector v. Of course, vector v is supposed to be non-zero vector. You cannot turn zero vector into a unit vector. So why it's going to be a unit vector? Let's calculate the norm of vector u. Well, norm of vector u, it's going to be a norm of vector v divided over norm of vector v. Well, because this is just a number, I'm going to take it outside of the norm. If you remember, we had a theorem where you can take the scalar outside of the norm, and I'm going to have 1 over a norm of vector v multiplied. What is going to be left is just norm of vector v, because this is norm. If I apply it to vector v, I'm going to get norm of vector v. And we do see that we have same numerator and denominator, and that's going to produce 1. So u is going to be a unit vector, and that's a valid way to turn any vector into a unit vector, right? Well, for example, if I want to turn into a unit vector, vector u2, I'll need to divide u2 by norm of u2, or u1, sorry. What is going to be? Let's consider example 3. Let's consider u1 equals 2, 0, 0. I know that unit vector is going to be 1, 0, 0, but if I use the formula, how it's going to work? Well, what is norm of vector u1? Square root. And if our inner product is defined as a regular dot product, we are going to have 2 by 2 plus 0 by 0 plus 0 by 0. In our case, that's going to be 2, right? And basically, a unit vector is going to be u1 divided over a norm of u1, right? And in our case, we are going to have 2, 0, 0 divided by 2. That's a norm. And we are going to have this 1, 0, 0 vector. Okay? Another definition. If a basis is orthonormal set, we are going to call this basis orthonormal basis. And we are going to use special letters to label vectors of that basis. E1, E2, En. So here vectors E are orthogonal to each other. I'm going to write it in I, E, J, right? And norm of EI, or all of them, is equal to 1. So what I'm doing, I don't want to write down that like they are orthogonal in pairs. I'm just writing down that any I vector is orthogonal to any J vector, and any I vector has norm equals to 1, orthonormal basis. Okay? Okay, good. Now the question is, why we actually care about orthonormal basis and how they are good. So let's write down the question. Why orthonormal basis is good, or better than just any basis? Well, remember that usually we need a basis to find the representation of a vector as a linear combination of vectors of the basis and use the coefficients of that linear combination as coordinates, right? Something like this. Usually if somebody gives us a basis S, which consists out of like n vectors, we represent vector W as, I don't know, C1, V1 by solving system of equations. Cn, Vn, right? And then we are going to say that vector W in basis S. Sometimes we are going to put square brackets around, which I don't have space to. Coordinates are going to be C1, Cn. But to find this C1, Cn, basically we need to write down a linear system. Remember, we are going to write down column of these vectors and solve actually for C1, Cn like we have for x1, xn. So basically we need to solve non-homogeneous linear system to find the coordinates, which can be kind of long problem, right? What is going to happen if instead of S, you have basis E1, En, orthonormal basis? How the situation is different? Imagine that I take the same vector w and represent it through this basis, as the normal one. C1 E1 plus Cn En, right? Well, here guys, I'm not going to solve a system of equations. What I'm going to do? I'm going to multiply both sides of this statement by E1. Let's watch what is going to happen. So E1 by omega. Well, I'm going to use a standard inner product here. So I'm going to have C1, which is a scalar, and then E1 by E1, then C2, E1 by E2. Well, I don't have a C2, maybe I should write it down, E2. And lots of them, and the last one, Cn, E1 by En, right? Now, guys, what is going to be inner product of E1 by E1? Well, since it's a norm of E1, right? And norm of E1 is equal to 1, just because it's orthonormal. Orthonormal basis. Now, what is going to be E1, E2? Well, I do know that E1, E2, because they are orthogonal, the dot product is going to be equal to 0, orthogonal. So, and all of these products are going to be equal to 0 except the only first term. And for the first term, we're going to have next equation. E1 W, our unknown vector, which we want to represent, find the coordinates. And because this is 1, I'm going to just have C1. So basically, guys, we have the answer for the first coordinate by just doing the dot product of our first vector of orthonormal basis with our arbitrary vector. And that's going to be true for all of them. So actually, C2 is going to be E2 by W. And C3 is going to be E3 by W. And we just can repeat the process. Just multiply the same equation by E2, E3, E4. The only one element which is not going to be equal to 0, because basis is orthonormal, is going to be the element which corresponds to the constant. Like if it's E2, it's going to be like C2, or E3 is going to be C3. And it's making our life much, much easier, right? So Cn last, oh, I should not put actually vector bar over C. Do it automatically. Is going to be En by omega. And that's going to be a legal way to find the coordinates. We don't need to solve systems of equations anymore. We just do like inner products or dot products if we wish. I'm going to consider one example of how we do this, because usually we kind of teach you how to normalize the basis, but like how to apply the normalized basis after. We need to see it also. Okay, let's consider orthonormal basis. Somebody gives us already orthonormal basis. So example number 4. So I'm going to write down E1. It's going to be not standard orthonormal basis. Give me a second. The coordinates are 1 over square root of 2, 1 over square root of 2, and E2. I'm going to check everything about this basis before I start working with it, so do not worry. So, somebody gives me orthonormal basis. Well, why should we trust that somebody? We are going to check if it's orthonormal. First, I'm going to check where it's ortho. So I'm going to actually find inner product, or in this case, it's going to be just dot product, because these are just two-dimensional vectors belonging to R2. I'm going to check whether it's orthonormal. So ortho. I'm going to do dot product between these two, right? 1 over square root of 2 by negative 1 over square root of 2 plus 1 over square root of 2 by 1 over square root of 2. You probably see that these two numbers are the same, just with minus, so it's equal to 0. So very good. So it's ortho. Is it normal? Let's find a norm of vector E1. So norm of vector 1, as you probably remember, is square root of the components, right? 1 over plus 1 over square root of 2 squared. And we are going to have a square root of 1 over 2 plus 1 over 2, which is going to be square root of 1, which is equal to 1. You can check it too by yourself, okay? Check by yourself. You're going to get 1. So this basis is orthonormal. Somebody gave me that basis, okay? And now somebody is asking, what are the coordinates of some vector v, which has normal coordinates 2, 1, in this basis S, which consists out of E1 and E2. Well, before I was supposed to solve system of equations. Now I'm just going to say that the first coordinate, C1, is going to be E1 dot product by vector V. And my E1 is 1 over square root of 2, 1 over square root of 2, dot product by 2, 1, which is going to be what? 2 over square root of 2 plus 1 over square root of 2, which is going to give me 3 over square root of 2. That's my first coordinate. And C2 is E2 by V. That's going to be 1 over square root of 2 with minus, I think, right? Let me double check. Where is my vector? Yeah, it has a minus over here. So minus 1 over square root of 2. And the same vector 1, 2, or 2, 1, sorry. 2, 1. Well, I'm going to have minus 2 over square root of 2 plus 1 over square root of 2, which is going to give me minus 1 over square root of 2. Now I'm going to combine them and say that V, the coordinates in basis S, are going to be 3 over square root of 2 and minus 1 over square root of 2. So no system of equations are supposed to be solved, right? That's very good. Okay, guys, so right now we do know why orthonormal bases are good. To find coordinates in them is very easy process. Now, how to find orthonormal bases? So, okay, blue. How to build well, I'm going to consider some bases and turn it into orthonormal. So way number 1, use some basis and turn it into orthonormal. Oh, how can we do it? Guys, I'm going to consider example of three-dimensional space and some bases in this three-dimensional space first, and then I'm going to describe your process in general, okay? So I'm going to consider that example, I don't know, number 5 probably, right? We're going to consider basis S, which is not orthonormal, just some basis in three-dimensional space, and I'm going to turn it into orthonormal. E1, E2, E3. What I'm going to do first, well, this is going to be like a process, and it's going to have some steps. I'm going to start with vector v1, and I'm going to turn it into a unit vector. So turn v1 into e1. Well, how do I do this? Remember, to turn some vector into a unit vector, we just need to divide it by the norm of that vector. So that's my first vector. Okay, done with vector 1, right? What is going to be next? Next, guys, we will need to find orthogonal vector. How I'm going to do it? I'm going to use vector v2 for that. I'm going to draw a picture. Imagine that vector e1 already, like, it was produced from v1, but it's already normalized. And there is a vector v2. Well, again, I'm drawing it geometrically, but nothing here is really supposed to be geometric. Well, guys, what we can do? We can represent vector v2 as two vectors. One vector parallel to e1 and one vector orthogonal to e1. I'm going to maybe label them as like w parallel plus w orthogonal. That's going to be my v2. And I'm going to explain how we do this, but before I explain it, and after that, we can use this orthogonal part, w orthogonal, and just turn it into a unit vector. And this way we are going to have e1 and e2 second vector. How we can do this like representation? Well, we already did this once, but maybe we'll need to kind of repeat it. Guys, I'm going to write down the formula for parallel part, w parallel. It's going to be dot product, or not dot product, but inner product of e1 v2, multiplied by e1 as a vector. How do I know that this vector is parallel to e1? Well, this is just a number. And it's multiplied by e1. So basically that's a vector e1 stretched or shrinked. I actually don't know. Well, you guys will probably see that that's going to be a parallel projection, but I don't really care if it's parallel projection or not. I'm just going to consider vector, parallel vector, which is like a e1, which is already like parallel to itself, right? And multiplied by some number. And this some number is going to be this one. And you will see why it's actually supposed to be this one, this dot product or inner product. I'm going to consider my orthogonal part as v2 minus this w parallel. So basically I'm kind of solving this equation for orthogonal part, moving this one to the left side. So it's going to be v2 minus e1 v2 by e1. The question is, how do I know that it's going to be actually orthogonal? The question is this what is supposed to be orthogonal? This one is actually going to be orthogonal to e1 because I multiplied by some number over here, right? Well, to check that e1 is orthogonal to omega orthogonal, we do it only once, guys. You don't need to repeat this logic of calculations every time if you understand it. So, question, are they orthogonal? If they are orthogonal, then the inner product between them must be equal to 0, right? Is it going to be equal to 0? Let's do it. Let's calculate it. And this is going to explain why the number I chosen is this. Let's calculate dot product or inner product. So I'm going to put e1 orthogonal. I'm just going to get this expression multiplied. And for this side, I'm going to have what? E1 v2 inner product, right? Minus e1 v2, this part I'm copying, multiplied by e1 inner product. Well, why this happens? When I multiply e1 over here, that's going to be product of these two, right? These two. When I multiply e1, it's got vector v2 by e1 here. Here, this part is not a vector, it's a number, because inner product is always a number. So actually, only vector here is e1. So that's why I multiply e1 by e1. So because my basis is orthonormal, I know that this one is equal to 1, right? And what I have over here is going to be e1 v2 minus e1 v2, which is going to be equal to 0. You see? That's why they are going to be orthogonal. Why did it happen? Because I have chosen the coefficient here exactly equal e1 v2. And now we just subtract it when we multiply it. You see? So the resulting vector is actually going to be orthogonal. And how do we find it? We find it by subtracting from vector v2 the parallel projection, actually, this. Okay, let's do it. I'm sorry, let's do it smaller and let's continue. Let's do it. So what I'm going to do, guys, I'm not going to label it W orthogonal. I'm going to label it V2 orthogonal part. And I already know the formula. It's going to be V2 minus E1 V2 multiplied by E1. So this vector is orthogonal to E1. We just checked it, it's orthogonal, right? But I'll need to make it orthonormal. So on my next step, step number 3, so I have V2 is orthogonal, but not normal. So here I'm going to make it normal or turn it into a unit vector. So my E2, my second vector, is going to be V2 orthogonal divided by the norm of V2 orthogonal. That's going to produce my second vector. How should I produce my third vector? Well, scroll it up. Now, guys, I'm just going to repeat the same steps. So I'm going to write down that V3 orthogonal, same way as I was doing V2. It's V3 minus E1 V2, V3, sorry, minus multiplied by E1. So I'm subtracting from V3 the part which is parallel to E1. And because I already have E2, right? I'm going to subtract also the part which is parallel to E2. So everything which is all parts of this vector which are parallel to this one and to this one are subtracted. So the remaining stuff must be orthogonal to these two. So we are going to get this one is going to be orthogonal to E1 and orthogonal to E2, which is very good, but it's not normal vector, and I'm going to normalize it, and I'm going to do it. E3 is going to be V3 orthogonal divided over norm of V3 orthogonal. Kind of long process, right? What if I have more vectors? 4, 5, 6, 7. Basically, guys, I'm going to repeat these two steps over and over again. I'm going to get next vector, and for vector v4, I'm going to subtract this term, and there's going to be one more term with my third vector. And that's going to produce fourth vector. So basically, the idea of the process is the next. You take any vector as the first one, normalize it, turn it into unit vector. And then take the second vector, again arbitrarily chosen, and subtract everything from that which is parallel to the first vector. And the result is going to be orthogonal. And then you take the third vector and subtract from it everything what is orthogonal, what is parallel to second and first vector. And that's going to be also orthogonal. And you can continue this process. What is interesting, guys, for this process, you normally don't even need to have a basis. You just can take like any vector as a starter and then use a second vector as like any vector which is not parallel to the first, and produce the orthogonal of the second vector. And then you can use a third vector, the one which is not linear combination of the first and the second, and kind of turn it into orthogonal. So normally, guys, you can build orthogonal bases even not just from bases, which is supposed to be linearly independent, right? You can build it from like any starting vector and any bunch of other vectors just by checking like certain conditions. Okay? Well, I'm going to consider example of two vectors, because with three vectors it's going to be an incredibly long process. But you can try three vectors, and we are going to try them in class. So, sorry guys, how do I erase it? Okay, so let's move it up and consider actually example of how to do really like orthogonalization of some bases. I'm going to consider example 6, and I'm going to use two vectors. v1 equals 1, 1, and that's going to be normal two-dimensional space with normal dot product. 1, 1, 2, 2 belong to R2 with standard dot product. Okay, so my goal is to kind of find orthonormal basis. So question, orthonormal. Well, what I'm going to do? Well, here guys, you can check independence of these two vectors, but they obviously look like independent just because they are not products of each other, and there are just two of them, right? In general, like if somebody gives you like arbitrary vectors, you better check like if they're linearly independent, because this is going to save you some work. If you get like vector not linearly independent of others, then your work is going to be wasted. You are not going to actually add the extra orthogonal vector. So, well, I'm going to do formal check. So I'm going to just have like 1, 1, and 2, 3. So first row, second row, find the determinant of this, and that's going to be 1 by 3 minus 1 by 2, which is going to be equal to 1, not equal to 0, so linearly independent. So these two vectors are linearly independent. Now, by my process, I'm going to do E1, which is going to be what? V1 divided over norm of V1. And that's going to be 1, 1 divided over a square root of 1 square plus 1 square. That's going to be 1, 1 over a square root of 2, and I'm going to turn it into separate coordinates. 1 over square root of 2, 1 over square root of 2. Very good. So the first one is no. Second one, V2 orthogonal is going to be what? According to my formula, it's V2 minus V2 E1 by E1. So I'm going to copy my V2. My V2 is 2, 3 minus dot. I'm not gonna apply the formula right away. I'm going to just first copy. So 2, 3 by E1. You already have to use this normalized vector 1 over square root of 2, 1 over square root of 2, and multiplied by 1 over square root of 2, 1 over square root of 2. Guys, here we have actually inner product, and here is just a vector itself. It looks like same. Well, let's just do this arithmetic. So I'm going to copy V2 and do this dot product. So 2 by square root of 2 is going to, I'm going to just calculate the number 2 over square root of 2, the first one multiplied, and the second one plus 3 over square root of 2, and multiplied by actually vector 1 over square root of 2, 1 over square root of 2. I'm very close to the end. So what I'm going to do, I'm going to add this 2 plus 3, and I'm going to get 5, right? 2, 3 minus 5 over square root of 2 multiplied by 1 over 2, 1 over 2. Well, it's going to be a couple of more steps. So let me scroll this up. Equals 2, 3 minus. Guys, what I'm going to do, I'm going to bring actually this number inside and multiply by each coordinate. So what I'm going to have 5/2. And the next one is also 5/2. Why? Because it's going to be easier for me to operate with this fraction. So now what I'll need, 2 minus 5/2, the coordinates, right? And 3 minus 5/2. Almost done. So here, for the first one, I have -1/2, and for the second one, I have +1/2. So this is my V orthogonal. The last step I'll need to do is normalize it. E2 is V2 orthogonal divided over norm of V2 orthogonal. So -1/2, 1/2, my vector, divided over norm. Norm is what? A square of each, right? So 1/2 squared. Here's supposed to be minus, but, well, I know that minus squared is going to produce just the vector itself, right? Plus 1/2 squared. And the square root. I'm very close to the end, and you probably see why 3 vectors is going to be much, much longer. I'm almost done. So what I have, 1/4 plus 1/4 is going to be 1/2. So the square root of 1/2. Now, dividing by fraction is multiplication by inverse, right? So square root, and I'll need to multiply it by, -1/2 and 1/2. I just have one last step, and that's if I, oh, sorry, I put a square root already here. It's not a square root, it's just 2. If I do this multiplication, I'm going to get a square root of 2/2 is minus, and the square root of 2/2, which is going to be -1 over square root of 2 and 1 over, sorry, somehow I keep missing the square. Well, that's my second vector. Now I'm going to write them down. So my basis now, well, I don't know, like S prime maybe, because it's a different one, right? Is going to consist out of 2 vectors. E1, which is 1 over square root of 2, 1 over square root of 2, and E2, which is -1 over square root of 2 and 1 over square root of 2. You guys probably already seen this basis. That was actually my first example where I was kind of finding the coordinates. So this is orthonormal basis. How I can be sure in this? I'm going to make it smaller and kind of roll it up and show you where I was actually checking it. You probably, guys, are going to see example number 4, orthonormal basis, and that's exactly it. So I got this orthonormal basis from 2 arbitrary vectors. Very nice. And I did check it over here that it's orthogonal and normal, and I even ask you to check vector E2 like at home. Well, that's it, guys. Three vectors is much longer process, but it's very similar to what we have with 2 vectors, and I think we can do 3 vectors in class. Okay, so let me finish at this point. And for those people who are more interested in theoretical part of why we can do that, there are a couple of theorems in this section 6.3 which are called projection theorem. You can read through this theorem, and kind of it's gonna explain you a little bit better like why we can do that. Okay, that's all for section 6.3.